Hey everyone, and welcome. Today, we're going to take a journey right into the heart of the atom to really understand one of the most powerful forces humans have ever managed to harness, nuclear fission. So it all kicks off with this number right here, about 200 million electron volts. That is the insane amount of energy that gets released when just one single uranium atom splits apart. To give you some perspective, that's millions of times more energy than you get from burning one atom of carbon from, say, coal. That's just a mind-boggling amount of power, and it's all locked up inside something you can't even see.
Which, of course, leads to the big question, right? How in the world do we get that energy out? What's the secret to unlocking this unbelievable subatomic power?
Well, the secret, as you've probably guessed, is buried deep inside the atom's core, the nucleus. Yeah, this is where all the magic happens, and it's where we're going to find our answers.
Okay, so this whole process, it's called nuclear fission. And put simply, it's just the act of splitting an atomic nucleus. But you know, this simple-sounding act has these massive consequences, because it doesn't just break the atom, it's literally turning a tiny bit of its matter directly into a huge blast of energy. So, to really get where all that energy is coming from, we need to talk about something called binding energy. This is the incredible force that holds the entire nucleus together. You can think of it like cosmic glue. It's the reason all those protons, which should be repelling each other, are stuck together in that tiny space.
Okay, and this is where things get really cool. The key to unlocking all this power isn't about breaking a bond like you would in chemistry. No, it's about a really fundamental connection between energy and mass itself.
All right, you've all seen this one, right? E equals mc², Einstein's famous equation. What it's telling us is that mass and energy, they're basically two sides of the same coin. A tiny amount of mass, that's the m, can be converted into a huge amount of energy, the E, all because you're multiplying it by c², the speed of light squared. And that number is just unbelievably massive.
And this is all thanks to that binding energy we just talked about. You see, heavy atoms, like uranium, they're actually less stable. They have less binding energy holding each particle. So when they split into smaller, more stable pieces, the total mass of those new pieces is just a tiny bit less than the original atom. That little bit of missing mass, it didn't just disappear. Nope, it got converted directly into pure energy, just like Einstein's equation said it would.
Now, here's a crucial detail. Not all uranium is the same. There's a big difference between what we call fissile and fissionable nuclei. Fissile stuff, like uranium-235, is special. It can be split by a slow, low-energy neutron just kind of drifting by. But fissionable stuff, like the much more common uranium-238, that needs a direct, high-speed hit from a really energetic neutron to split. And that single difference is why U-235 is the star player in most nuclear reactors.
So what does this split actually look like?
Well, you can think of it like this four-step subatomic dance. It's pretty elegant, really.
So check this out. First, a slow neutron just wanders by and gets sucked into a uranium-235 nucleus. For a split second, this creates a new, super unstable nucleus, uranium-236. It wobbles around for less than a blink of an eye before it just splits apart into two smaller pieces that fly off at incredible speeds. And this is the absolute key to the whole shebang. Along with all that energy, 2 or 3 brand new, fast-moving neutrons get kicked out. You see, those neutrons that just got spit out? They're the secret sauce. They are the very first domino in what can become an unbelievably powerful domino effect.
And that domino effect has a name. It's called a chain reaction. It's a process that can sustain itself. The neutrons from one split go on to cause other atoms to split, which release more neutrons, which cause even more splits, and on and on and on. It's this incredible cascade of energy release. Now, this chain reaction, it can go one of two ways. If every split causes on average more than one new split, the reaction grows exponentially. It runs away. That's a bomb. But if you can engineer it just right so that each split causes exactly one more split, then you get a perfectly controlled, steady release of energy. And that is a nuclear reactor.
So, okay, that's the multi-billion-dollar question, isn't it? How do you actually tame that atomic domino effect? How do you keep that reaction perfectly, and I mean perfectly balanced, to generate power safely, day in and day out?
Well, it turns out we have a few really clever tools to do just that. First, you have moderators, usually water, that slow those speedy neutrons down to the perfect speed for U-235 to grab them. Then you have control rods.
These are made of materials that just love to soak up neutrons, acting like a brake pedal you can move in or out to fine-tune the reaction. But the real secret weapon, the thing that makes it all controllable, is something called delayed neutrons. You see, a tiny fraction of them don't pop out instantly. They come out seconds later. And that little delay gives our control systems and human operators the time they need to keep everything perfectly stable.
And the goal for any reactor is to reach a state called criticality. Now that word sounds kind of scary, right? But in nuclear terms, it actually means perfect balance. It's that sweet spot where the chain reaction is exactly self-sustaining. It's not growing, it's not shrinking, the power output is totally constant, and the reactor is just humming along, safely making electricity.
And that really leaves us with this incredible duality, doesn't it? As the saying goes, the discovery of fission gave humanity a new fire, one with the power to light the world or to burn it. The physics is simple, the choice is not. Understanding this incredible science is really the first step toward making that choice wisely. Thanks for joining me on this deep dive.